All right, friends. So today we're going to talk about ionic and covalent compounds, which I know that you read about on Monday, and you might have had some questions about that when you were doing it on your own. So I'm hoping that this little review with me will help you piece together anything that wasn't making sense on Monday when you were looking at those at the handout that I left for you. So first, just to review valence electrons, we talked about this in the last unit. They are equal to the group number. We do leave off the transition metals when we talk about the representative elements, we call them. And so the number of valence electrons is equal to the group number. So 1, 2, 3, 4, 5, 6, 7, 8. Helium is an exception. Helium is actually happy with only 2 valence electrons instead of 8. But most things are looking to achieve that octet. In terms of what a valence electron is, remember it's electrons that are in the highest energy level. We call that the outer shell. So if you were drawing this as a Bohr model, these would be electrons that are in the outermost energy level. So the first thing I'll talk about are ionic compounds. So ionic bonds are between metals and nonmetals. So hopefully you saw that on Monday on that intro handout. So you have something on the left side of the periodic table. When you look at it, those are the metals. And then it's bonding with something on the right side of the periodic table, a nonmetal. And we talked about in this first part that metals tend to lose electrons to react. And so that ability to lose that electron determined reactivity. What we didn't really talk about are that nonmetals react by gaining electrons. And so together, when a metal reacts with a nonmetal, the metal is losing its electron actually to the nonmetal, okay? And so in that way, electrons are transferred from the metal to the nonmetal. So you can imagine this is going over to the fluorine. Another thing to note here that you saw on Monday are these Lewis dot structures. So a Lewis dot structure puts a dot for every valence electron that's in the compound. So for potassium, we know that it has 1 valence electron, and that 1 valence electron is drawn as a dot. For fluorine, fluorine has 7 valence electrons, 2, 4, 6, 7. Okay, so again, that came from the group number that we saw on the last page. All right, so we have electrons that are being transferred between metals and nonmetals. When they transfer, an ionic bond is formed, and an ionic bond is the attraction between positive and negative charges. We actually saw that when we started talking about Coulombic attraction in the last unit. So when things have opposite charges, there's what we call an electrostatic force that really holds them together. So when potassium loses 1 electron, it becomes +1 because it has 1 extra proton. When you compare it to electrons, it has 1 more proton than electrons. And when it transfers that extra electron to fluorine, remember, now fluorine becomes -1. So it has 1 more electron than it had before. And so now it is F-. And again, the attraction between them is this like force between positive and negatively charged particles. So covalent bonding is different. Covalent bonding happens between 2 nonmetals. So both, obviously, these are the same thing, but 2 nonmetals, so 2 different elements from the right side of the periodic table. In this case, electrons are not transferred from one element to the other, but they're actually shared. They become like a pool of electrons that both of those atoms can use. So for instance, in this case, again, if each element is looking to achieve an octet, which is 8, for this compound, they could achieve that by each sharing 1 electron. And the one that they share goes in between the 2 atoms that are sharing it. Then the electrons that are in between here, again, because it's like a pool, they're available for this chlorine on the left, and they're available for this chlorine that's on the right. So they become like communal. The pair that is shared between them, again, one from the chlorine on the left, one from a chlorine on the right. This is called the bonding pair. It is also called a single bond. So a single bond is made of 2 electrons. And when we draw that as a structural formula, anytime there's a bond, the dots become a line. So 2 dots is a single bond. So 2 dots becomes 1 line between each atom here. And so we have just made a chlorine molecule, Cl2. Again, you're filling this out on your handout as we go through this. So if you need to pause because I go faster than you can write, you're welcome to do that as we go. All right, what about something like oxygen? So each oxygen has 6 valence electrons, 2, 4, 5, 6. And then the other one on the right also has 6. So if it were to share only 1 valence electron between the 2, notice they would still both be unhappy. So these become communal. So the one on the left has 2, 4, 6, 7. And this one has 2, 4, 6, 7. So 7 is not an octet. So that would not work. So in this case, they would actually need to share more than 1 between the 2 of them. And so if they were to each share 2, then we would have a double bond. So we have 2 bonding pairs, so we would make a double bond. When we draw the structural formula for that, again, those bonding pairs become lines or dashes in the structural formula. So just a quick review again, the difference between ionic bonds and covalent bonds. Ionic bonds are made of metals on the left side of the periodic table and a nonmetal on the right side of the periodic table. So you can really tell what kind of bond it is by looking at the location of where these elements are in the periodic table. With ionic bonding, it does involve electron transfer. And when that happens, we get charged particles. So we get ions that form. You get positive ions for the metals and negative anions for the nonmetals. In terms of their properties that they have, and we'll explore these a little bit next week, ionic bonds are brittle and they have really high melting points based on the way that they arrange themselves based on these charges that they have. Some examples would be sodium chloride and lithium fluoride. Something to note, and something you saw on Monday in the handout, is notice when they become a compound, the charges go away. So like sodium chloride, sodium transfers an electron and becomes Na+. Chlorine accepts that extra electron and becomes becomes Cl-. But then when they come together, again, it's neutral. So there's no charges in that overall formula. And that's because when they come together in this 1-to-1 ratio. Because if I have 1 positive for every 1 negative, I have an overall 0 charge. And so when we make an ionic bond, we always want the charge overall to be neutral. Covalent bonds are made of 2 nonmetals. So these are 2 elements that are both on the right side of the periodic table. They do share electrons rather than transfer. So for this, there are no charges. And this isn't really writing for me. Try again. No ions. So no charges when they're sharing. And you could have single bonds, double bonds, or triple bonds in this case as well. You also saw on that handout on Monday that, these covalent bonds, nitrogen and oxygen can come together in a variety of ways because they're not ions, which is different from ionic bonds. Like sodium chloride is only NaCl. one sodium and one chlorine. There is no other ratio that they can come together. So different from covalent bonds, which do have a little bit more of a variety of ratios that they can come together since they're not made of charged particles. When we look at covalent compounds, we notice that they have lower melting points. They do not conduct electricity, and they are softer. Example would be carbon monoxide. And so you did see on Monday as well, when we name these, we use prefixes to denote how many of each of these elements are in the compound for covalent bonds, since we don't know the defined ratio, since they don't have charges. Okay. All right, hope that was a helpful review. I did also want to show you something else. So in terms of what you were supposed to do without me, hopefully this simulation went really well. I think it's really designed pretty well. So hopefully you didn't have any questions about that. For Lewis dot, again, those number of valence electrons is equal to where those elements are in the periodic table, what group they are, and then however many they have becomes a dot in the Lewis dot diagram. The number of electrons needed to make an octet, well, you always need 8. So you're seeing how many away from 8 it is. And then in terms of the ion, if you lose electrons, you become positive. And if you gain electrons, well, then you're overall negative charge. So depending on how many you gained or lost, that's how you would know the charge there. Yeah, hopefully that made sense. I feel like I talked through the idea of, ions versus not ions. Where are they in the periodic table? You're supposed to mark them. So carbon and oxygen are both on the right side. So they're both made of non-metals, whereas this was metal, non-metal. Yeah, so hopefully that makes sense. Down here for ionic or covalent, you're looking to see where are those elements in the periodic table. If they're metal, non-metal, it's ionic. If they're both non-metal, then it's covalent. Okay, and then the last thing I wanted to show you is how to do a Lewis structure. So in this unit, we are really focusing on these covalent compounds. So we really won't get to ionic compounds until we start to do reactions towards the end of the semester. So first, we're just going to really talk about these covalent compounds. And again, those covalent compounds are 2 or more nonmetals that are coming together and sharing electrons. And so when we're trying to decide, like, how do they bond, how many lines do they have, how many dots go in the structure, we do have a very defined step system of how we put those molecules together. There are other ways of approaching it, but I do feel like this is probably the most straightforward. So if you go down these steps every time you bond these covalent compounds, you really can't do it incorrectly. So it's only when people start to try to do it on their own and they don't go make sure they're going down every single step here, that's when they start to make mistakes. So I would just say, especially in my absence, when you're first putting these structures together, make sure that you're going down every single step, 1 through 7. And then, yeah, you should be doing a great job if you really go through each step. Okay, so H2O, how many bonds does it have? How will it bond? How do we know? So I'm just going to go through each of these steps with you for a couple of these. So H2O, it says first I need to count the total number of valence electrons. Okay, so for hydrogen, there are 2 of them. and there's one oxygen. In terms of valence electrons, each hydrogen has, actually, let's do that again. There's 2 hydrogens and there's 1 oxygen. And there's 1 valence electron for each hydrogen. And for oxygen, there are 6 because oxygen is in the 6th column. So the 6th group in the periodic table. So that means we have 2 coming from those hydrogens and we have 6 coming from the oxygen. So a total of 8. Okay, so I did my first step. Then it says I need to choose the central atom. So it's usually the thing that's written first. However, it can never be hydrogen because hydrogen is happy with only 2 electrons rather than 8, like most other elements. And it is also never going to be a halogen. So if it can only bond 1 time, it really can't be the central atom. So in this case, I know it's not hydrogen because that's an exception. So my oxygen is the central atom. If oxygen is the central atom, I then surround it with the 2 hydrogens. Okay. Then it says attach all peripheral items to the central atom with a line indicating a single bond. Okay, so I have 2 lines. Then it says subtract the number of bonded electrons from the total number of valence electrons. So each line is 2 electrons. So that's a total of 4. So I have 4 left. I fill in the remaining electrons to the outermost atoms until octets or duets are satisfied. So hydrogen again is an exception. So hydrogen is happy with only 2 electrons. That's called a duet. So even though there are 4 valence electrons left, I'm not going to put those on the hydrogen because once the hydrogen bonds, that's it. That is 2 electrons for each of those hydrogens. So my remaining 4 will have to go on the central atom. Because the next step says once all peripheral atoms have fulfilled octets or duets, any remaining electrons go on the central atom. Then it says if the octet's not satisfied for the central atom, make multiple bonds. So in this case, when I check, and I'll use a different color, the hydrogens are happy with 2. We said over here, this hydrogen has 2 from the line, because remember, if they're in between the 2 elements, they're shared. This hydrogen has 2 as well. And then my central atom has 2, 4, 6, 8, because remember, it is able to use those shared electrons as well. So all the octets and duets are satisfied. I don't need double or triple bonds. Okay. Let's try that again for N2 because it does look a little different. Again, we're going to do all these steps in order. Okay, and I really want you to do that. This entire worksheet, don't try to just freestyle. You're not ready for the freestyle yet. You really have to practice going through each step before you're able to do that. Okay, so for N2, it says count the total number of valence electrons first. So there are 2 nitrogens. Each nitrogen has 5 valence electrons. So times 2 is a total of 10 electrons. So that's my total valence. Then it says choose a central atom. Notice there's no central atom if there's only 2. So I just have N and N. Attach peripheral atoms to the central atom with a line. So I attach. I subtract the number of bonded electrons from the total. Remember that each line is equal to 2 electrons. So minus 2 means I have 8 left. Then it says to fill in those remaining electrons until the outermost atoms have octets or duets satisfied. So I'm going to put them together in pairs. So you'll never have one by itself. So 2, 4, 6. So now that nitrogen is happy because it has 2, 4, 6, and then 8 from the one that's shared in between. So my last two, I'm going to put on the nitrogen over here. So now I'm done. Now there's 0 left. So there's none to put on the central atom, and there is no central atom. Then it says if the octet's not satisfied for the central atom, make multiple bonds. So in this case, there's not a central atom. However, when I add them up, this nitrogen has 2, 4, 6, 8, which is great. But notice the one on the other side only has 4, 2, 4. So that's not going to work. In this case, I will need double or triple bonds to make my octets work. So when that happens, you have to remove electrons that are already in the structure, okay, and make them shared pairs instead of unbonded pairs. So I'm going to move these 2 electrons here. So now they are no longer up there. So does that work? Well, now the one on the left has 2, 4, 6, 8, but the one on the right still only has 6. So it's still not satisfied. All right, again, this is 8, but this side only has 6. So I will need to do that again. I will need to remove 2 more electrons that are already in the structure and make it a bonding pair instead. And now when I check, I see each nitrogen has 8. So this nitrogen has 2, 4, 6, 8, and this nitrogen has 2, 4, 6, 8. Okay, I will post the key to this later. So as you're doing them, you should make sure that you're doing them correctly, but really give it a go on your own before you go and just like copy this worksheet or copy the key just to get it done, because you really do have to make those trial and error mistakes as you're working through it, because really that's how you learn the method of how to put these together. So when we finally have a summative assessment for this, you are not given these steps. So eventually these steps are committed to memory in terms of how do I actually, draw these structures. All right. So you should finish the rest of these in class today and then submit those in Canvas tonight. All right, email me and let me know if you have any questions. Thanks, friends.